Let us now go through the steps in selecting a battery for a given application. First, we need to identify and select a battery chemistry for the given application. What it means is that do we need to select a lead acid battery, or should we select a lithium polymer battery or a sodium sulfur battery, etc. Now we need to make the decision based on the application, whether the application needs lithium polymer or lead acid, or is lead acid sufficient, whether the availability of that particular battery is easy or not in that locality, and of course the amount of capital available to invest on the battery. Now these are considerations that you need to take, and then based on that you select a particular battery type, battery chemistry. For most of the applications, especially if it is not on a mobile platform, and if it is for solar photovoltaic applications where real estate is not an issue, because anyway you need real estate for the PV collectors, one can start off by going with lead acid batteries, lead acid tubular batteries, because the capital investment will be lesser. Next, find out what is the allowable depth of discharge for the particular battery. Now this is an important parameter that you should know, because this will tell you what is the ampere hour rating of the capacity or the capacity of the battery that you will finally have to select. Now the depth of discharge also depends upon the chemistry and the type of the battery that you will be choosing. The lead acid battery, for example the SLI batteries, start lighting ignition, which are used for cars, vehicles. They have very high power density requirement, but the energy density is low. They have a depth of discharge of around 20% only. So you don't select this type of battery for continuous discharge, continuous low discharge current type of applications. Now if you take the lead acid tubular battery, they are good for continuous low discharge applications. Here the depth of discharge can go as deep as 80%. Lithium polymer batteries can go to 80%, but normally 70% is chosen. So when you want to go for these deep discharge batteries, your application also should equivalently dictate the need for such deep discharge batteries. If the discharge currents are low but continuous for a very long time, then go for deep discharge batteries. If the discharge currents are very high and very short time, then go for batteries like the SLI batteries. Next, find out what is the watt hour requirement of the load. We need to know this. We need to know what the watt hour of the load is in order to decide on the capacity of the battery. Next, let us calculate the capacity that is required, so that you may choose a battery of a particular ampere hour rating. Now if you take a battery like this, and then let us say that the depth of discharge that we have found out for that battery is around so much. This is the DOD of the battery. Then this shaded portion is the usable watt hour, or this is the watt hour that can be given to the load, and this whole capacity is what you have to rate the battery for. That will be the watt hour of the battery. So watt hour of the battery is watt hour of the load by DOD, depth of discharge. And the ampere hour rating of the battery would be watt hour rating of the battery divided by the battery voltage, nominal battery voltage. So if you take for example a lead acid battery containing 6 cells, you will say the V battery nominal is 12 volts. Next, let us select the C rate for the battery. In order to select the C rate, let us consider this graph. On the x-axis, I have T, the discharge time in hours, and on the y-axis, the discharge current ID in amps. Let me now mark an arbitrary operating point in this ID versus T coordinate system. I will take an arbitrary operating point like this. I will explain what that is. So this operating point is the intersection of some discharge current ID here and some time in hours. So this area here would be the amp hours, and let us consider this point for now. Let this point indicate a particular C rate. Now at values of discharge currents lower than this operating point, I have drawn a straight line here, and it is following this relationship, which is I into T is equal to a constant C, constant capacity C. And then here at discharge currents above this particular selected discharge current, it will follow some kind of a square law pattern. Now that relationship is I square T is equal to C, the capacity here. Now consider this operating point here. Let me mark that, and with respect to the operating point, all this area here, let me say is 100 ampere hours. Let's say this area here is 100 ampere hours, which means I can have, let us say for this example, 5 amp. This is the discharge current, 5 amp, and for 5 amps we have some discharge time 20 hours. So for 20 hours we have 5 amps flowing, resulting in 100 ampere hours passed on to the load, and we can say this is a C20 rate battery operating in this fashion. Now let us say you want to choose somewhere here 10 hour. Will you get still 100 ampere hour capacity? No, you will get something lesser, because now you are trying to discharge more current in lesser time. So let us say I have discharge time as 10 hours and you have chosen a battery. Now the discharge current here would be at approximately, let us say 7 amp. It is not going to 10 amp. So this area, that is the ampere hour that is passed on to the load, is 70 ampere hour. So this operating point is now, let us say, at C10. So a battery, a C20 battery, if it is operated at C10, the capacity is reduced. It is reduced to 70 ampere hours instead of 100 ampere hour. So as you start going higher and higher in discharge current, lesser and lesser time results, and therefore the capacity also reduces. It is not same as what you started off with the C20. So at low discharge currents, you could have the model as a straight line. IT is equal to C, capacity is equal to I into T. As the discharge current becomes higher, then you have to use a square law pattern for the model. I square T is equal to C. So you will have a model for C rate choice, something like this. And then knowing the value of the discharge current, you can appropriately choose the C rate for the battery. So find out the average ID or the peak ID depending upon what the application demands and what is important for the application, and appropriately choose the C rate from the I to the power of n into t is equal to constant curve. So this we can say I to the power of nt is equal to constant, and that constant is representing the capacity. So n is a varying quantity, so we say n is equal to 1 for low discharges. ID is low, so here we have used n is equal to 1. So at low discharge currents we have C is equal to I into T, simple ampere hours. And for high discharges we use the square law, n is equal to 2 for high discharge currents, ID being high. So here in these regions you have I square T is equal to C for the discharge currents which are larger. So using this kind of an approximate model, you can select the C rate for a battery for given discharge profiles.